Um, Good evening to all of you. Yesterday we had the first session of thermodynamics and we discussed various concepts related to work done. And today, what we are going to do is we are going to discuss the first law of thermodynamics and we'll have a few discussions on that, and then there will be some homework on that. So, So all of you know that according to the first law of thermodynamics, the change in internal energy is equal to heat absorbed plus work done on the system. So whenever there's a system and heat is being given to the system, so that is Q, and the work that is being done on the system is W. So change in internal energy is Q plus W. Now the thing is that in laboratory conditions the external pressure is usually constant because it is the atmospheric pressure, so you can just replace W with minus PEX into delta V, because in laboratory conditions PEX is usually constant. Now so delta U is U2 minus U1 and delta V is V2 minus V1. So this is the corresponding equation I have written, and now we can say that Q is equal to U2 plus PEX into V2 minus U1 plus PEX into V1. So U2 minus U1 is Q minus PEX into V2 minus V1. So Q will be U2 plus PEX into V2 minus U1 plus PEX into V1. So this PEX is something which is going to come again and again. For simplicity, instead of PEX, let us just write P. So for simplicity, let us just write P because we are going to write it again and again. So U2 plus PV2 and U1 plus PV1. Now this quantity U plus PV okay, this quantity U plus PV, this is called the enthalpy or the heat content of the system, right? Literally, enthalpy means heat content. So this quantity U plus PV is called the enthalpy or the heat content of the system. So H is equal to U plus PV is the heat content of the system. So this expression, it will be called suppose H2, and this expression is called suppose H1. So Q will be H2 minus H1, or you can say delta H. So keeping pressure constant, the difference of in final and initial values of U plus PV is called the change in enthalpy. Okay, so keeping pressure constant, the final value of U plus PV minus the initial value of U plus PV is called the change in enthalpy delta H. Okay, so we can also say that the change in enthalpy of a system is equal to heat supplied at constant pressure, because in this expression, both the expressions we are having the same value of P. So heat supplied at constant pressure is equal to change in enthalpy. And one more thing, is that if you go to the equation of the first law, you know that work done is zero for isochoric process. So isochoric process means constant volume. So that means the heat absorbed at constant volume is equal to change in internal energy. So once again, the um, the heat absorbed at constant volume is change in internal energy, and heat supplied at constant pressure is equal to change in enthalpy. Now, one important thing you have to remember is that, like internal energy, we are always concerned with the change in enthalpy. We are not concerned with the absolute value of enthalpy. We are always concerned with the change in enthalpy. What is the change in enthalpy is what concerns us. Just like internal energy, we are always concerned with the change in internal energy. Now, the thing is that there are certain reactions in which the reactants and products are both gases. So, suppose A is the reactant and B is the product. So this is the reaction. So what you can do is that if the reactants and products are both gases, you know PV is equal to nRT. So P delta V is nR delta T. So delta H is delta U plus nR into delta T. Just replace P delta V and write nR into delta T. So actually it is delta nRT, and I'll write G because to suggest that we are only talking about gases. See, when you say pressure, it means the pressure of the surroundings, that is atmospheric pressure, and when you say temperature, temperature of the surroundings. So more or less that is expected to be constant. So delta H is delta U plus delta Ng into RT. So what is delta Ng? It is a change in number of mole of the gaseous substances. So this is also gaseous, this is also gaseous. So the difference in number of moles, that is delta Ng. So this is another alternative version. So we have delta U equal to Q plus W, that is the main statement of the first law. You can say that a corollary of this is delta H is delta U plus P delta V, that is a corollary of this. And this corollary has a sub-corollary that if they are all gases, then delta H is delta U plus delta Ng into RT. In case there are substances which are not gaseous, then you must not count them in delta Ng. In delta Ng, you must only count those which are gaseous. Okay. Okay, now we come to the molar specific heats. You see what happens is, I have told you that QV is equal to delta U, that is heat absorbed at constant volume is change in internal energy. I have told you that QP is equal to delta H. So heat absorbed at constant pressure is change in enthalpy. Now delta H is delta U plus P delta V. I can now introduce the molar specific heat at constant pressure, that is denoted by Cp. So delta H will be number of moles into Cp into delta T. Similarly, delta U will be number of moles into Cv into delta T. And since PV is nRT, so P delta V will be nR delta T. So just remove, uh, P delta V and write nR delta T. So if you cancel n delta T, Cp is Cv plus R. So Cp is molar specific heat at constant pressure, Cv is molar specific heat at constant volume, and the relationship between them is Cp equal to Cv plus R. Now regarding this Cp equal to Cv plus R, you must remember one thing, that Cp divided by Cv is gamma. So you can write like this: gamma Cv is equal to Cv plus R. So Cv will be R divided by gamma minus 1, and Cp will be gamma into R by gamma minus 1. So if you replace Cp is gamma into Cv here, gamma Cv is Cv plus R, so Cv is R by gamma minus 1, and Cv will be gamma R by gamma minus 1. Okay, now the thing is that you have certain categories. Monoatomic, diatomic, polyatomic. So for monoatomic, Cv will be 3R by 2, for diatomic 5R by 2, and for polyatomic it will be 3R. Then Cp will be 5R by 2, this will be 7R by 2, and this will be 4R. So you have to remember these values. For monoatomic, Cv is 3R by 2, for diatomic 5R by 2, polyatomic 3R. For monoatomic, Cp is 5R by 2, diatomic 7R by 2, and polyatomic is 4R. So these are the values of Cv and Cp for mono, dia, and polyatomic gases, right? So these are the values. Okay. Okay, now just a couple of things I want to tell you, that in the last session we discussed isothermal work done. So the formula was minus 2.303 nRT log V2 by V1 base 10. So because it is isothermal, instead of V2 by V1 you can also write P1 by P2. So minus 2.303 nRT log P1 by P2 base 10. You can write this also. And if it serves your purpose and if it is convenient, you can do one more thing. Instead of nRT in these two formulas, instead of nRT, you can also use PV. If it is convenient to use PV, you can do that. Just replace nRT with PV. So this is for isothermal work done. Okay, another thing is regarding adiabatic processes. Uh, Whenever there is um, expansion, the isothermal graph will always be above the adiabatic graph whenever there is expansion. But whenever there is contraction, the isothermal graph will be below the adiabatic graph. This is a very important information which will help you to compare isothermal and adiabatic. And one more thing you must remember that um, when you are discussing adiabatic expansion, it has got a unique feature. Adiabatic expansion results in cooling, and adiabatic contraction results in heating. So adiabatic expansion results in cooling and adiabatic contraction results in heating. So this is a very special feature of adiabatic expansion and contraction, right? So that takes care of this particular session of the first law of thermodynamics. And now what we'll do is that I'll just give you some homework questions based on this. Okay, all of you, these are the homework questions for the next session. Question number 1, you take 1 mole of carbon dioxide and you take it from 10 liters at 300 Kelvin to V liters at 150 Kelvin, and the process is adiabatic. 1 mole of carbon dioxide, you have to take it from 10 liters 300 Kelvin to V liters 150 Kelvin adiabatically. Question is, what is V liters? Options are 20, 40, 80 and 5. Question number 2, you have to take 1 mole of ammonia from 300 Kelvin 100 decimeter cube to T Kelvin 800 decimeter cube, and you have to do it adiabatically. So what is the work done and what is the temperature? What is W and what is T? So the options are 900 Kelvin, 900 calorie 150 Kelvin, 900 calorie 300 Kelvin, 1200 calorie 150 Kelvin, and 1200 calorie 300 Kelvin. These are the options. Question number 3, you have to take a 1 mole of monoatomic gas from state 1 to state 2. State 1 pressure 4 bar, volume 22.7 liter. State 2 pressure 2 bar, volume 3 liter. What is the work done? Options are minus 1729 joule. Option B 1729 joule. Option C minus 75.8 joule. Option D 17.07 joule. Question number 4 is from the JEE Advanced 2013 paper. Pressure volume graph is given KLMN. You have to identify from K to L, is it heating or cooling? From L to M, is it heating or cooling? Is from M to N, is it heating or cooling? From N to K, is it heating or cooling? Question number 5 is from JEE Advanced 2012. P1, V1, T1 and P2, V2, T2 are, if you take the gas through process 1, which is isothermal, and P3, V3, T3 if you take it through process 2, which is adiabatic. So you have to select which are the correct options. More than one is correct. First option is T1 equal to T2. Second option T3 greater than T1. Third option isothermal work is greater than adiabatic work. Fourth option change in internal energy for isothermal is greater than change in internal energy for adiabatic. So these are the homework questions for the next session, which will be at 9 p.m. tomorrow. And if you submit within that time, you can engage in a meeting and discuss your homework. So I'll end this particular session. I'm concluding it now. Bye.